This is problem number 8 on page 98. A fisherman yanks a fish vertically out of the water with an acceleration of 2.5 meters per second squared. Using a very light fishing line that has a breaking strength of 22 newtons. The fisherman unfortunately loses the fish as the line snaps. What can you say about the mass of the fish? In this problem, as in most problems, you'll do well by making a sketch and writing out what you know. In this problem, we've got a fish being yanked out of the water. This should be fun to try to draw a fish. Here's our fish getting pulled out of the water. And there's a line pulling the fish up. We, of course, know that's the fishing line. And forces in lines or strings or ropes we call tension. You can abbreviate that with a capital T, or you could also write F sub T, whatever you want to do here. We also should recognize that on this free body diagram we have the weight of the fish. That can be written as mg, or you could write that as F sub G, whatever you want to call it, or W. All these are kind of equivalent ways of notating the weight of the fish. If I wanted to, I could have just sketched kind of like a separate free body diagram instead of that sketch. So, you know, the fish becomes a box. And I think when you do it this way, what might be a little bit better way of drawing this is showing that this tension vector going up has to be larger in magnitude than the weight vector going down. We know that because the net force, the mathematical sum of T and mg in this case, is upwards. So T needs to be larger than mg. We know that because the fish is accelerating upwards. All right, so let's put this over here and start our problem. I'm going to write an equation in the vertical plane by starting by saying, is the sum of the forces in the y plane equal to 0? The answer to that question should be no, and our evidence for that is that the fish is accelerating vertically. So therefore, I'm simply going to look at my free body diagram and basically write it algebraically. I'm going to say that tension, which is a positive force based on the idea that things that go up are positive and things that go down are negative on that convention. And then I'm going to subtract from that the weight, mg. I'm going to set that equal to, instead of 0, since we know that the sum of these two is not 0, we've answered that in this previous step, we're going to say that it's equal to some leftover force, the net force. Now we can basically expand this idea of net force over here into its component parts. We can say that, well, we know that F net is also equal to ma, so I'll write that here. And we're left with T minus mg is equal to ma. In this case, I'm going to group these like terms. Ultimately, I'm going to be solving for mass, so I'd like one instance of mass. I'm going to add mg to both sides. I get T is equal to ma plus mg. Factoring out an m from those terms on the right-hand side, I get T is equal to m times a plus g. Solving for m now, I get m is equal to tension divided by the sum of the acceleration of the fish going upwards plus gravitational acceleration, little g, which we know is 9.8 meters per second squared. No need in this case to include a negative sign. Let's go ahead and move this stuff over here. So our last step involves a numerical substitution. We know that the max tension here is 22 newtons. That's given to us in the problem. We also know that the acceleration of the fish is 2.5 meters per second squared upwards. We're going to add to that 9.8 meters per second squared, and that's equal to our mass. Plugging those numbers in yields about 1.7 kilograms. So our final answer with correct significance is going to be 1.7 kg, and that's equal to our mass, and we're done.